All right, welcome to another screencast, and here I am social distancing, but getting this screencast done on, we're in subtopic 6.2 for IB, which is Newtonian's law of gravitation. And Newton's law of gravity here has some important terms that I'll just make sure we get. IB calls this R, and it really should be D. It's the distance between centers. So the point of this question is two human beings that are like standing near each other. The distance that you would put in there for R is the distance from the center of the mass, which would be like in the exact middle of the person over to the exact middle of the other person. And that distance between the two people, the centers of the masses of the two people, is what you put in for R. We talk about treating every mass as a point mass. In the definition of the universal gravity law here, we would talk about M being a point mass, means that we're assuming that the mass of the whole object is at a single point, and that point is going to be located at the center of mass. Notice that means that there's no way for D to be zero, because if it's at the center of mass for me and at the center of mass for Nan, then there's no way for D to be zero, because even if we hug as hard as we can, the center from me to the center from her is still going to be a few centimeters. And so that way you can't think of R going to zero and F getting really big, because there's always going to be some real distance between the two centers of mass since they're taken as point masses. So like when I put in capital M here with 80 kilograms for capital M, it's thought of being at a single point where the location of the center of my mass would be. And then for Nan, her mass, 60 kilograms, little m there, also would be at the center of the mass. And the distance between those two point masses is given by D, or in this case, with the IB equation, they like to use R. And in this equation, it's in the denominator and it's squared. So this is called an inverse square proportionality, sometimes called an inverse square law. And gravity acts that way. And what that means is if two objects are twice as far away, force of gravity would be 4 times less. If two objects are 9 times farther away, then this force will be 81 times less. And so that gives you the ratio. Capital G is dependent on the units used. Okay, this is like a fundamental constant of the universe, and its number is empirical, which is empirical means that you calculate it using labs and figure out what the number is, but it's the same everywhere in the universe. It would change if you had different units. So the number we use, which is down here, 6.67 times 10 to the negative 11th, has units of newtons, meters squared per kilogram squared, and it has to be in those units. So when you use mass, you have to use kilograms. When you use R or D in the denominator, you have to use meters, and the answer you get here for F will be in newtons. You can imagine a different society or culture, and they use different units. They would have a different value for G, but it's actually the same constant in the entire universe. It's simply that you'd have a different number for it because you had different units. Notice one thing. G has meters on top, 2 of them. See the meters on top, 2 of them. That cancels the meters on bottom in the D squared, right? The units of G cancel the units of R. The other units of G are in the denominator, kilogram squared. So G has units in the denominator of kilogram squared. And that cancels the 2 kilograms up here, you know, the 80 kilograms and the 60 kilograms. So the kilograms disappear. All the units get canceled away because the units for capital G are just right to cancel them away. And N is the only unit left. And that's why force over here will have to be in newtons, which is appropriate since it's Newton's, universal gravity law. Excellent. We'll be doing more with these equations next time, but I put them here just to remind myself to mention why we use R instead of D, because for this equation and what we're doing in this problem of the day, we would think of it as D, the distance between my center mass to Nan's center mass, 30 centimeters, that is D. And we put it in for R here, but the reason we do for R is in 6.2, we do a lot of stuff with orbits, we do things with planets, and often the value that you're using in the denominator there is a radius of a planet or something like that, or of an orbit. And so they have R there for that reason. But in problems like this one, it's really more of a D. And let's look at how the math, it's very easy, plug and chug. You got a couple things to be careful of. Make sure the mass is in kilograms, which it is. Make sure the distance is in meters, which it is not. So the 30 centimeters have to turn over to meters, which is done here. And then just make sure you plug this into your calculator properly, not messing this up. And I just did this. Hopefully I didn't mess up, but that's the answer I got just now. It should make sense that this is a tiny number. Gravity is the weakest of the forces in nature, in the universe. Gravity is the weakest force. So it takes things like planets and stars with huge masses before we start to really see gravity force in our lives. So the gravity force, the force of gravity attraction between the two of us is like just a few millionths of a Newton. So there might be other forces of attraction. That was a joke. But there's not much gravity force of attraction. And that's because G is such a tiny number, times 10 to the negative 11th. And I suppose I should exponent that up. Okay, so I helped us a little bit with the basic ideas in this screencast with how to use this equation. It is very much plug and chug. It can have more than, this is when we have two masses and not just one mass, and I'll talk about that in the next screencast a little bit about, well, what's going on if you're just talking about the Earth by itself and not two objects. So this equation is used when we have two objects and we'd like to know the force of attraction between them. And in the definition, always make sure that you mention point masses, the inverse square law, and the fact that the force is attractive and not repulsive, which is obvious, but everybody always forgets to say, oh, it's attractive force when you write the definition. Anyway, hopefully that helped. I'm trying to go a little slow. Maybe I'm going too slow, I feel like. Anyway, I'll go a little faster on the next one. And that was a pretty easy 6.2 DDD. Hopefully that helped you out a little bit.